Hello YouTube, RJ. In this third in a series on Introduction to Digital Electronics, as I promised, I created the circuit that we designed in our previous video onto our breadboard. And we've got a Arduino Nano wired up to two 595 chips. And we've got the LEDs as promised. And I wrote some software, and now I want to demonstrate what we've been looking at in the previous videos. So if you haven't looked at those videos, you might want to pause. You might want to go back and look at the Introduction to Digital Electronics, the part 1, part 2, where we discuss all the different facets of digital electronics for the intro, and we explain what this circuit's all about that we designed. And now we're going to actually walk through and go from the showing it theoretical in paper to real world, walking through and demonstrating the data moving on our circuit here. What I'm going to do is download the software and start it. What happens is when we do that, the system's going to load and come up and ask me what I want to do. And if you look right here, it's wanting to know I can enter 0, 1 to add, meaning if I want to clock in a bit, a high or low into my data chain, I can do that manually. I can do 3 to clear the registry, which all the registers are cleared when you start the program, so we're already there. I can turn the output enable on or off. 4 is off, 5 is on. That is the OE. Notice the line over it. Remember, that means low. If it's low, the output's enabled. Currently, if you look at these LEDs, remember our LEDs that show us the status of the data lines. Notice that the OE is low, the light's off, so the output enable is already on. And then 6 is auto-populate alternating 1s and 0s. And what that does is instead of me manually 1 bit at a time putting it in, it puts a 1, a 0, 1, a 0, 1, 0 until it fills up all 16 registers. And it starts out slow and it speeds up. So you can see what's going on in the beginning, but you can start seeing how quicker and quicker we can make it run. And so that you understand, while you're going to see things happening very slow on this board, in real world, if you were designing a controller for this, it would be almost instantaneous as far as you could tell, because all this would be clocking at a high data rate. We're doing this real slow. Sometimes we'll be like a second between cycles. Most of the time it'll be about half a second, but you'll be able to see the LEDs coming on and going off. And the software will tell us what it's fixing to do and have me push a key to say, okay, we're ready, we're watching for it, do your thing. And we're gonna walk through. So the first thing we're gonna do, we want to clock a 1 into the first shift register. And again, if you haven't watched the other videos, this isn't gonna mean a lot to you. So I highly recommend you go and review those videos and then come back and watch this one. What we're gonna do now is, if you remember your chip design, you've got your shift registers in one column and you've got your storage output registers over here that actually turns on or out the ports. What we're going to do right now is we're going to tell the system to clock a 1. Everything is clear. Clock a 1 into the shift registers, which would be the first channel up here. We're going to have it clock a 1 in. It then will clock it from the shift register out to the output. And since we have the output enable on, you'll see it actually come on. So let's tell it we want to do 1 and enter. And it's going to say, okay, I'm ready to set the data high. Here's our serial data line, this LED right here. And so we're going to hit enter. We should see it turn that on because it's going to set the data line high. It wants to input a high into the register. So it's going to set the data line high, which it did. Now the software says, okay, I'm ready to clock it into the shift register. So now now what we have to do is we have to generate a clock cycle up and down on the SR clock line, remember, and that will shift whatever's on the data line into the register, into the first shift register in the series. And remember, the top chip, first register, second, third, fourth, right on down, and then it daisies over with one data line into the second chip and continues on. So we're going to be telling it to clock in that high into the first register on this chip, the top chip, which is the top LED here. Now, it's not going to light that LED. Remember, this is clocking it into the shift register. This is not then shifting what's in the shift registers out to the actual storage registers. So let's tell it go ahead. It went high, it went low. That clocked the data in. So right now the first shift register on that first chip has a 1 in it. Now the storage register doesn't have anything in it because we haven't put it there. Now it's ready to turn this back low again. We don't need it high anymore. So I'm going to go ahead and do that. Data went low. Now what's going to happen is it's going to ask me to clock the shift registers all into their storage registers. So what we're looking for here is the R clock, the registers clock, the actual storage registers. This should do a high then low to clock it in. There it goes. And when it clocked it in, notice that this one came on. Now it's wanting to know what I want to do. So now let's send a 0 in. Let's put a low in. And what's going to happen is that same action is going to happen again, but we're going to clock a 0 into the first register, which will push the 1 we put in into the second register. Again, they're shift registers. We're going to shift this 1 to the register 2 and shift the 0 into 1. This is going to move. I put a 0 in, enter. Ready to shift, set data low. Data's already low, but it's going to set it low. It's ready to shift it into the shift register, so we should go high and low here. We did. Notice nothing changed here. Of course, our storage registers do not change as we change the shift registers. Only when we clock the R clock high and low does all the shift registers load into our storage registers. So now it wants to take data line low, already low, but it's going to take it low. Now we're ready to do the R clock. We're ready to clock what's in the shift registers over to the storage registers, the outputs. And right now the outputs are set with the first register high, but our shift registers aren't. Our shift registers are set with register 2 high, register 1 low. But once we do this shift, it's going to move what's in those shift registers over to the outputs, and you're going to see it change. So we're going to do that now. It did it, and notice what happened. We pushed a 1 in here, or 0 into the first register, so that pushed that 1 into our second register. We can do this again. Let's do another 0. And now that 1 is on the third register, not the first. We've pushed 2 zeros in. So let's push a 1 in. I'll step right through. If you watch, you'll see the same pattern happening. Now we got a 1 in our first register. And now that 1 we put in originally is in the fourth position. So this is what we described when we described and looked at the data sheet and talked about how the circuit was going to work. Now, what happens if I want to clear all the registers? Okay, now I can put a 3 in. If I want to clear everything, I can put a 3 in, and it's going to say it's ready to clear all registers, and it's not going to wait for me. It's just going to go do it all. But what it's going to do, it's going to take and drop the SR clear low. You'll see this. Notice this has been on the whole time. That's because for the chip to operate, your storage register clear needs to be held high. If you make it low, it clears all the shift registers. I'm saying storage, I mean shift. It's going to clear all the shift registers. So what's going to happen is I'm going to drop this, bring it back up. That's going to clear the storage. And then what I'm going to do, if you notice, you'll watch the R clock will cycle to put those cleared registers over into the storage registers so all the registers are cleared. So here we go. It went down, went up. Notice everything's off now. Everything's back to clear. We're back to the state we started in. So what we can do now is I'm going to do 6. Now what 6 is going to load alternatively 1 and 0, 1 and 0, 1 and 0, 1 and 0 until it fills the registers out. So it'll alternate every one of them. So you'll end up with a 1 at the very beginning, 0, 1, 0, 1, 0. It's going to do this. It's going to run right through and do it for me. It'll clear everything first before it does. But if you watch, it'll go very slow when it starts. You can actually watch the data and watch the pattern and how it's doing it, and it'll speed up as it goes. So you can kind of, by the time it gets to the last few, it's going to really move quickly. Here we go with 6. Clearing the register and starting to send the data now. There's a 1. Now it goes low here. It's clocking in a 0. Now a 0, it shifted it in. high, it shifted it in. Now it's going to shift it in. Over and over again. Each time it clocks a new one in, and notice it's picking up speed. Going faster and faster. Going to get really quick now. Here it goes, and the last one's boom, boom, instantly. What we can do is let's talk about the output enable. We haven't played with that yet, but remember the output enable is when you pull it low, it enables the output. Okay, it's been low pretty much all the time. But if you wanted to shut that off, maybe you want those lines to be turned off while you're making a change, or maybe you want to turn them off because you want to let other chips hooked to the bus of these connections control those lines, and you don't want to pull them low or pull them high. You want to say tri-state, as we talked about, and let other items on the bus on these data lines control these lines. We would want to use the OE to do that. And so what we do is we'd want to pull it low. So would want to disable the outputs. So if you look at my software, if I do 4 will do that. So let's do 4 and enter, and it's ready to do it. And I'm going to enter, and notice the output enable went high and all the outputs went off. They're all tri-stated now. They're not being pulled low. They're not being pulled high. We can have other devices connected to these lines controlling things. Now, if I want to turn, nothing's changed in the registers. They've all stayed the same. The data is just the way we left it. So if I now go in and instead turn the enable back on, so if I do 5 and enter, you're going to notice it drops from a high state to a low state on the OE, which it's enabled when it's low. That's what the line above it. Remember that. When it re-enables, you'll see that the lights will all come back on because those lines go active. Whatever's in the storage register now turns on. We changed nothing, so we have the same thing we had before. This is really it. I hope this is a simple demonstration. Hopefully it makes sense to you. That's it. That is the premise of digital electronics. Obviously, this all happens at very high speeds. You can load, you could daisy chain, 20 of these chips, and from what you visually could see, we can load and bring them on faster than you can see. That's the 595, but all digital chips work similar. This is not just about the 595. This is about how digital electronics works, and I hope you've learned something. I hope you've enjoyed this video. If you got any questions, feel free to ask in the comments. If you enjoyed it, do me a favor, take the second to hit the like button. It helps me greatly. I appreciate it. If you're not subscribed and you'd like to see more of my videos, hit the subscribe button. It does take a minute, doesn't cost you a dime, and you can always unsubscribe anytime you want to if you decide you don't want to be subscribed. But the most important part of it all is, as always, hope to see you in the next video.